In this video, we're going to start Chapter 9, Approximate Methods for Multiple Degree of Freedom Systems. In this chapter, we're going to discuss kinetic and potential energies in multiple degree of freedom systems, Rayleighs Quotient, and Dunkerley's formula. And in this video, we're going to focus on the first two sections up to including Rayleighs Quotient. So far, we have examined multiple degree of freedom systems and seen that to solve for natural frequencies and mode shapes, they are essentially eigenvalue problems. In some cases, we don't care about all of the natural frequencies, but rather the lowest, or sometimes the largest, natural frequency of a multiple degree of freedom system. So there are methods that allow us to find these frequencies that don't require solving all of the frequencies. So first we need to discuss kinetic and potential energies in multiple degree of freedom systems. So let's consider an n degree of freedom system with generalized coordinates qi, where I goes from 1 to n, describing a displaced configuration of the system. Each qi could be linear or rotational displacement. So q is the vector of these generalized coordinates, q1 to qn, and q dot is the derivative of these coordinates. These represent the coordinates and their derivatives, which are where the derivatives are either linear or angular velocities. For linear systems, the potential energy in the system is given by U is equal to 1/2 Q transpose KQ, where K is the stiffness matrix. Similarly, the kinetic energy, T, is equal to 1/2 Q dot transpose MQ dot, where M is the mass matrix. So this allows us to discuss something called Rayleighs Quotient. So for a conservative multiple degree of freedom system, the total mechanical energy is a constant. So T plus U is equal to some constant amount of energy, E. So using the relationships for the potential and the kinetic energy, we can write this expression here. Now let's consider the system vibrating in one of its normal modes at a natural frequency p. The amplitudes of the coordinates are given by this expression. Q is equal to phi, a sine pt plus phi, where phi, big phi, is the mode shape and a is a constant. The derivative of the coordinates will be given as shown here. And now the coordinates all reach their maximum value when sine pt plus phi is equal to 1, and they're given by q max is equal to a phi. At the same instant, cosine pt plus phi is equal to 0. Similarly, the derivatives of the coordinates will all be a maximum when the cosine pt plus phi is equal to 1 and are given by q dot max is equal to a p phi. So let's consider equation 9.3 when sine pt plus phi is equal to 1. In this case, the kinetic energy goes to 0 and the potential energy, the coordinates become their maximum. So we have 1/2 q max transpose k q max is equal to E. And we can replace q max with a phi, as we shown on the previous slides, which we can rearrange as shown here. So similarly, when cosine pt plus phi is equal to 1, the potential energies go to 0, and the q dots become their maximum. So these q dot max can be replaced by a p phi, as shown here. And we can rearrange this. So given that this is a conservative system, the total energy is a constant, and 9.6 and 9.7 can be compared to give this expression. And now we can simplify this, canceling out the a squareds as well as the 1/2s, and rearrange it to get the expression here, where p squared is equal to phi transpose k phi divided by phi transpose m phi. Now this formula is known as Rayleighs Quotient, and it allows us to estimate this natural frequency p squared. Now, this may not seem useful, as we often use K and M to find the mode shapes corresponding to natural frequencies to begin with. And in Rayleighs quotient, we need to use the mode shapes to come up with our p squared. So it's actually most useful for providing an approximate natural frequency for an assumed mode shape, phi. So we assume a mode shape, and then we use the mass and the stiffness matrices as given in the expression to come up with an approximate value for the natural frequency p. The better the guess of phi, the more accurate the natural frequency, but it can actually be shown that for any assumed mode shape phi, the natural frequency p returned by Rayleigh's quotient will be greater than the lowest natural frequency and smaller than the largest natural frequency of the multiple degree of freedom system. So this allows us to understand the bounds of the natural frequencies for any and using any given mode shape. But the better the guess, the more accurate the natural frequencies will be.